Hello, my name is Rick. My supervisor is Dr. Carlos Rossa. We are from Oshawa, Ontario, and we are presenting electrical impedance tomography using differential evolution integrated with a modified Newton-Raphson algorithm. Electrical impedance tomography, or EIT, is a medical imaging procedure. It is a fairly inexpensive procedure when compared to methods like X-ray and MRI. It is a non-invasive imaging procedure as it does not involve inserting medical instruments into the patient. How it works is you would have electrodes placed around the medium of interest, whether it be a water tank like in the picture above or the chest of a human baby. And the idea is to inject electrical current through a pair of electrodes and then measure the resulting voltage from the rest of the electrodes. The idea is to switch up the pattern so that you have different injection sites and measurement sites so that you can have enough voltage measurements that you can reconstruct the internal resistivity of the medium of interest. And the applications range from cranial imaging of newborn babies, lung imaging, or breast imaging for breast cancer. The problem of EIT is very nonlinear and ill-posed, meaning that there are way more unknowns than there are knowns. The unknowns being the resistance values that you're trying to solve for in the electrical circuit, and the knowns would be the boundary voltages that you measure. EIT is usually solved using an iterative fashion using two approaches, the forward solution and an inverse solution. In the forward solution, you're trying to solve for the boundary voltages knowing the current injection and the internal resistance distribution. In the inverse solution, it's much harder because you're trying to solve for the internal resistance distribution knowing the current injection and the boundary voltages. There are different ways to solve for the forward and inverse solutions. For the forward solution, these range from using Kirchhoff's current law to finite element modeling. For the inverse solution, there are different deterministic and stochastic methods, which we will talk about in the next slides. Deterministic methods usually involve placing a specific input and getting an output that will be the same usually every time that you run it. An example of a deterministic method would be modified Newton-Raphson. It usually runs faster than stochastic methods. However, it does require an initial estimation to start the algorithm off, and this estimation has to be close to the true distribution of the medium of interest, or else the results may not converge or it might produce a result that is not acceptable. In the case of stochastic methods, these are algorithms like differential evolution and particle swarm optimization. They rely on randomness to be able to solve the problem at hand. They can avoid convergence and local minimas, but they are usually more computationally heavy and more complex than deterministic methods. Our proposed method is a combination of deterministic and stochastic methods, which we will explain in the later slides. It basically integrates a deterministic method like the modified Newton-Raphson into a stochastic algorithm like the differential evolution. So it does not need to have an accurate initial estimation in order to solve the problem. In our paper, the problem is modeled as a square electrical circuit of finite size. S denotes the amount of electrical nodes that we have in the circuit. All the resistance values are stored in a vector of R. The current source is stored in a vector of I, and the voltage readings are also stored in a vector of B. And then to solve for the boundary voltage values, we would take the inverse of the conductivity matrix, which is an inverse of resistance, and then multiply that with the current injection to solve for the boundary voltages. I will start by explaining the modified Newton-Raphson algorithm, and then I will explain the differential evolution algorithm, and then finally our hybrid method at the end. How the modified Newton-Raphson algorithm works is it is an iterative procedure that initializes with an estimation of the resistance distribution. You would then calculate the boundary voltages knowing that resistance distribution, and then obtain what is called a Jacobian matrix, which we will explain in the next slide. And then using that Jacobian matrix, we would update that initial estimation of the resistance distribution that we initialized it with, and then we repeat this process until our initial estimation is very close to what the true resistance distribution is, and that will be considered our final answer. And then that is when the modified Newton-Raphson algorithm would end. In order to update our resistance distribution each time, we need an error term, and that is defined here mathematically. And all that it is essentially the difference between the calculated boundary voltages and the measured boundary voltages. The measured boundary voltages are obtained from the physical setup, as in around a water tank or around the chest of a human baby. And the difference is taken into this equation to calculate for the error that we're going to be used in order to update the resistance each time in the modified Newton-Raphson algorithm. Updating the resistance is simply just adding a delta RK term into the current resistance vector in each of the iterations of modified Newton-Raphson. And we'll explain how to get that delta RK term in the next slide. Essentially, it will keep repeating this process until the calculated boundary voltages are very close to the measured boundary voltages. And as I stated before, when this algorithm starts, the R naught term, or the very first initial resistance distribution, needs to be very close to the actual true resistance distribution in order to produce acceptable results. Sometimes this is feasible, but in most of the cases, getting that accurate initial estimation is a challenge and may not be feasible in all cases. In order to solve for the error equation that we defined earlier, we differentiate it with respect to R, and we set it equal to 0. And when we do that, we will have a Jacobian matrix, which is the derivative of all the boundary voltages with respect to all the resistors. And what this Jacobian matrix shows, it basically shows how sensitive each of the voltage values are if we change a specific resistor that's in the resistor circuit. And if we substitute and rearrange that equation, we can solve for the delta RK term, which can be represented as a function of the Jacobian matrix, the boundary voltages, and the identity matrix. The lambda and the identity matrix is there to mitigate the ill conditioning and singularity of the problem. Now we move on to explaining the differential evolution algorithm. The DE algorithm is a population-based stochastic optimization algorithm, and it starts with randomly generated individuals. The population is made up of all these individuals, so each row in the population P is a candidate solution, and then each column in this matrix P is a specific resistor that we have in the electrical circuit. The DE algorithm is categorized into 5 distinctive steps, and the flow of the process can be illustrated with this figure on the right. So you would start off by initializing all the algorithm parameters. You would generate new individuals through the mutation process. You perform the crossover step, and then get to the selection stage where you select the individual that is more fit, and then you will repeat this process until your parameter conditions have been met, and then your final most fit individual will be the solution to the problem. For our paper, the initialized parameters include the number of individuals, generations, runs, the mutation, the crossover factor. In the mutation step where a new mutant vector is formed, we are using the DE rand1 format. There are different mutation formats, and this is just the one we selected. And how it works is you will create a new mutation vector based off of 3 randomly selected individuals from the population, and it depends on a phi, which is the mutation factor that we have selected. Once the mutant vector is generated, we move on to the crossover stage. We are using binomial crossover for our crossover process. And how it works is we generate a crossover vector that will or may or may not take on the shape of the mutant vector, and that depends on a random number C and the epsilon value, which is the crossover factor. And then once we have this crossover vector, we move on to the selection stage, where the algorithm takes a look at the crossover vector and the target vector that's currently in the algorithm in the population. And the algorithm will choose the vector that is more fit and then discard the other one. And then this process is repeated for every individual in the population for a fixed amount of generations and runs until the final conditions have been met and the algorithm stops. Now we move on to explaining our proposed hybrid algorithm. In the proposed algorithm, it is slightly different than traditional DE algorithms in the sense that it optimizes each of the outputs from the mutation stage with the modified Newton-Raphson, and also the crossover process is a little bit dynamic when compared to traditional DE, as the crossover factor actually changes depending on the fitness of the crossover vector, and I will explain that in the next slides. The modified Newton-Raphson algorithm is integrated into the mutation step of the proposed algorithm. So after the mutation stage occurs and the mutation vector is generated, this vector is fed into the modified Newton-Raphson algorithm as the initial estimation of the resistance distribution. And when the modified Newton-Raphson algorithm optimizes that initial estimation, the output goes into the crossover stage. The crossover factor actually changes between 0.1 and 0.9. If the output of the modified Newton-Raphson is fit, meaning it is a good candidate solution, the crossover factor will become 0.9, where the vector will take on the form of the Newton vector. Whereas if the output of the modified Newton-Raphson is very poor, the crossover factor will become small, like 0.1, and the crossover vector will then resemble very little to the mutation vector. And then this is carried on into the selection stage of the proposed algorithm. So to simulate our proposed algorithm, we created a true distribution that is mostly made up of 20 ohms with 60 ohms center in the middle. And we ran the differential evolution algorithm by itself, as well as the modified Newton-Raphson algorithm initialized with different initial estimations. And then we ran our hybrid algorithm. And the parameters are displayed in table 1. And I will show you the results on the next slide. So as can be seen from the images on the right hand side, the most fit results are produced by the modified Newton-Raphson algorithm and the hybrid method. Each simulations yielded different fitness values. A low fitness value means that the calculated resistance distribution closely matches that of the true distribution. The modified Newton-Raphson was initialized with 3 different distributions: 30 ohms, 70 ohms, and 100 ohms. The 30 ohms initialized simulation produced the best results because it is most close to the true distribution of 20 ohms, whereas the 100 ohms yielded a fitness value that was very high, and it was not able to identify the middle concentrated mass. The differential evolution was not able to converge to a solution in the given parameter. The hybrid produced similar results to the modified Newton-Raphson when initialized with 30 ohms. However, the hybrid did not require an accurate initial estimation in order to execute the algorithm. So in conclusion, different inverse algorithms were explored in this paper. The modified Newton-Raphson was initialized with 3 different resistance estimations: 30 ohms, 70 ohms, and 100 ohms. The 30 ohms was proved to be the best result as it was most close to the true distribution. The differential evolution algorithm was not able to produce acceptable results, and the hybrid method is proven to be superior to the modified Newton-Raphson, as it does not require an accurate initial estimation but was able to produce very similar results to a 30 ohm initialized modified Newton-Raphson algorithm. This is the end of the presentation, and thank you for listening.